Good morning. I am Santosh Ramagya. This work has been done by Dr. Suraj and myself under the guidance of Professor Amit Agrawal and Atul Sharma. And I am going to present for investigating dragonfly flight dynamics at various saving amplitude of its wing. And this presentation is for full paper. Why should study dragonfly flight? The dragonfly flight is important from the perspective of making micro aerial vehicle. This is the micro aerial vehicle which has been made at the Harvard Micro Robotics Lab, and it has applications in my rescue operations and so on. And the second thing is Dragonfly, from fundamental fluid dynamics point of view, it has applications in the studying the unsteady fluid dynamics at the low Reynolds number. Let's briefly look at the forewing of a dragonfly. This is the forewing of a dragonfly, and this is the hindwing of a dragonfly. The dragonfly, if you take a cross section of a dragonfly wing, the cross section profile is corrugated, and the corrugation profile varies in the spine-wise direction. So we have taken a midsection of a dragonfly wing, which is this, and this can be modeled into this kind of a foil, which is called dragonfly inspired corrugated foil. Let's review some of the representative airfoil section covering the transitional range of Reynolds number. At the lowest Reynolds number, we have rough airfoils, which belongs to Dragonfly class, and the smoothness begins to be imported from the Reynolds number range of 50,000 onwards. At the lowest Reynolds number, roughness is important to delay the flow separation, and whereas smoothness begins to be important from this Reynolds number range, which belongs to the pigeon class, bird class. And further, if we measure the performance of an airfoil can be measured in terms of the ratio of lift by drag. For rough airfoils, the performance increases monotonically, whereas for smooth airfoils with reduction in Reynolds number, there is a steep change in performance of smooth airfoil. This steep change is because of flow separation. So we can define a critical Reynolds number of 70,000. This critical Reynolds number can divide an airfoil of insect class, which is of the Reynolds number of 10 to the power 4, and airplane class, which belongs to the Reynolds number of 10 to the power 6, 1 million. So what we have done, we have studied a smooth airfoil and rough airfoil. This rough airfoil belongs to insect class, and the smooth airfoil belongs to a dragon is airplane class. And further, we have studied for two different angle of attack, where this is negative angle of attack, this is positive angle of attack. If we study if you look at the parameters affecting the flow field for the heaving and pitching foil, so there are these many parameters which affect the flow field, and where Reynolds number and reduced frequencies are defined as this. So what we have done, we have fixed the pitching amplitude, and we have varied these many parameters in order to investigate the performance of pitching and heavy foils. So parameters for the experiments and simulations are inspired from a live dragonfly data. The range of radius frequencies or Reynolds number are as mentioned in this slide. So what we have done, we have taken two foils and taken two different studied at different Reynolds number. The reduced frequencies and heaving amplitude are as this for a fixed pitching amplitude, and the chord length of the foil is 50 mm. The experimental setup is consists of a water tunnel. This is the water tunnel which has been used in the PIV measurement. The schematic of the PIV setup is as follows. Where this is the green, this is the laser sheet, this is the camera. At the bottom, at the top, we have a servo motor in order to pitch the foil. With this motor in turn is controlled by the controller, and the computational domain is as shown, where we have used ANSYS fluent-based simulation, and for turbulence and laminar model has been used at the respective Reynolds number. Pressure velocity coupling, we have used piso algorithm. For pitching foils, at the reduced frequency of 5.48, we can see the formation of reverse one Karman wave for both the foil, where there is an excellent agreement between the numerical and experimental results. This validates the numerical results, and there is the lift coefficient for corrugated foil is higher as compared to the NACA foil. With further increase in reduced frequency, the state jet starts to deflect downward for corrugated foil, whereas the jet is horizontal for the NACA foil. This shows the lift. This indicates further that the lift coefficient is higher for corrugated foil. If we look at further, the mean velocity profile, the mean velocity at the lowest reduced frequency, as usually we have deficit wake. Then further, with increase in reduced frequency, we have a momentum excess wake. With at the highest reduced frequency, where the jet is deflected downward. And for heaving foils, let's study the vorticity field variation with respect to heaving amplitude. At the lowest heaving amplitude, there is no vortex shading for corrugated foil, where there is vortex shading for NACA foil. With further increase in heaving amplitude, the intensity of vortex intensity increases, and with this for NACA foil at heaving amplitude of zero point 0.3, we can see the formation of dipole vortex. This we will discuss further in more detail. And whereas this at 4.5 amplitude, uh, at heaving amplitude of 4.5, both the vortexes are merged in order to form a single wake. This is 2s plus 2s arrangement, which will be discussed in more detail in the further slides. And further, with the increasing heaving amplitude, the intensity of both leading and trailing edge vortices increases. So here, at heaving amplitude of 0.430, there is a formation of secondary vortex within the corrugation of corrugated foil, whereas there is no such secondary vortex is observed for corrugated this NACA foil. And 2s plus 2s wake, which is called dipole vortex, dipole vortex, dipole wake for NACA foil, is observed. And with further increase in heaving amplitude, the strength of secondary vortex is more for corrugated foil. And this secondary vortex gives the second harmonic in the lift coefficient. If we perform the FFT analysis on the lift coefficient, FFT is basically an acronym for fast Fourier transform. FFT is an efficient tool in order to investigate the periodicity of the flow. So at the lowest heaving amplitude, we get there is only one dominant frequency present. With increasing heaving amplitude for corrugated foil, we have a secondary frequency. There is a second harmonic, and with further increase in heaving amplitude, the second harmonic is evident for NACA foil as well. With further increase in heaving amplitude, with both so primary as well as secondary harmonic increases in its strength. Further, with in the mean velocity profile, is as usual we have at the lowest heaving amplitude, there is virtually momentum less wake for corrugated foil, whereas for NACA foil there is a momentum excess wake, which is indicative of thrust production. So with further increase in heaving amplitude, the thrust production capability increases, whereas the wake width is higher, wake is wider for corrugated foil. If we summarize the performance of both the foils in terms of this force coefficient, this is thrust coefficient and this is lift coefficient. Negative thrust means drag. With increase in heaving amplitude, the thrust coefficient increases for corrugated foil as well as NACA 0012 foil, whereas where the thrust coefficient is higher for NACA 0012 foil. So here we can say that corrugated foil is not outperforming the NACA foil in terms of thrust coefficient, whereas if we see the lift coefficient is 0 throughout up to 0.6 for NACA 0012 foil, because the wake is symmetric and the foil is also symmetric. At the highest heaving amplitude, the lift coefficient is slightly negative. It has a non-zero value because of the secondary vortex, and there is slight deflection is observed in the jet. Whereas for as far as lift coefficient of corrugated foil is concerned, it shows a non-monotonic increase in lift coefficient, with the highest value of lift coefficient is observed at 0.75 heaving amplitude. So to summarize, in the bottom left, there is a critical heaving amplitude beyond which there is an existence of secondary vortex for both the foils. However, because of the corrugations, the critical value of H is lower for corrugated foil compared to NACA 0012 foil. And the secondary vortex is responsible for the existence of second harmonic in the FFT of the lift signal. Momentum or thrust of corrugated foil is lower compared to Naka foil. This shows that dragonflies are inefficient in terms of thrust production. They most of the time they're inefficient in thrust production compared to the smooth foil. Dragonfly inspired corrugated foil is inefficient in terms of thrust production. So here we suggest that corrugated foil can be used. Implementation of corrugated foil for UAs would be more helpful in terms of lift rather than thrust. Thank you.